So, rearranging functions, and we're going to focus, the main aim of this thing is to look at logarithmic functions or power functions, which we can then use logarithms to get them to look like straight line graphs. So it's all about power functions, really. Here is an example of a relationship that might well be a power function. So if you wanted to have a look in the textbook, it's on page 269, work problem 1, but let's have a look at it. We've got a function here, but it's an x squared function, so y equals ax squared is the function. So we suspect this function, we believe this function is related by an x squared law. That's what it says here. We think it's an x squared relationship, so related by it in this way. So if we plotted a graph, we could check that it's that sort of relationship, because if we plot it, and I've done this on autograph, we get what looks like a curve. And it looks as though it might well be a quadratic function, because that's a sort of shape of curve that you get with a quadratic function. So you guess that it's an x squared relationship, and that's part of it, really. From a knowledge of the situation that's creating these results in the first place, and also a knowledge of what graphs look like, you could guess you've got this sort of relationship. So if you think it is an x squared relationship by plotting this graph and getting the curve, you then plot a second graph. If I assume this is an x squared relationship, instead of plotting y against x, I plot y against x squared, which is my guess. If I'd guessed it was an x cubed relationship, I'd plot y against x cubed, and so on. And then if my guess is correct, I'll get a straight line. So in other words, in this particular example, y has been plotted, so y on this axis has been plotted against x squared, and we can now confirm our guess is correct because we get a straight line. So that confirms that the relationship is of the form y equals ax squared plus b, which is what we get in this first case, y equals ax squared plus b. So once we've done this graph, we can actually find the values for a and b. Because if we plotted y, which we've done, against x squared, then we've got a line that looks like y equals mx plus c. So in other words, once I've got a straight line, the gradient of this line is going to give me the value for a in the relationship, and the y-intercept is going to give me the value for b in the relationship. So all I do is draw the straight line. I'll sort of do it as best as I can through here. It looks like the y-intercept is around about 8 or 9, something like that. But if I have this autograph software to hand, I could zoom in on this and find the value for the y-intercept. So I could zoom in on this point here. I could also find the gradient of the line by plotting that straight line like we did before. Put the line y equals mx plus c and adjust it until it goes through the points. And so effectively we're finding this gradient. And then we've got the values for m and c. Okay? So that's okay. We guess that it's an x squared relationship. Try plotting x squared and see what happens. We might guess it's an x cubed relationship. Try and plot it and see what happens. What we could do with a better method than that, really, rather than guessing what the relationship is, we could do with a way that allows us to come up with the number that we're going to try. And this is where logarithms come in. Let's look at another example. Here's one where the current flowing in and the power dissipated in the circuit in a resistor is measured. So we've got current against power that's being plotted. And we assume it's some sort of power relationship. So this is the power relationship. The power is related to the current with some sort of power, n. We don't know what that power is though. So we're going to use logarithms to try and rearrange this formula so that it looks like a straight line, y equals mx plus c, the equation for a straight line. So that's what we need to do. We need to think now about logarithms and what they mean and how we can use it in this case. We've looked at logarithms before, and as a reminder, if we've got something like y equals 10 to the power x, then the logarithm to the base 10 of x is y. That's the definition of logarithms. The logarithm to the base 10 of y is the power to which 10 is raised to get y. That should read the x there. The logarithm to the base 10 of x is the power to which 10 is raised to get y. We've got that the right way around. Logarithm to the base 10 of x, yeah. So I'm turning my value of y into a power. If y equals 10 to the x, then log to the base 10 of x is y. Let's look at an example of this as a reminder. Example. Find the logarithm of 5 on your calculator. So the log of 5 is 0.699. So what does that mean? The logarithm of 5 is the power to which I raise 10 to get 5. So I have actually written that the wrong way around, haven't I? The logarithm of the base 10 of just like the way you say it that I'm confused with at the moment. In other words, 10 to the power 0.699 to 3 significant figures should give 5. Yeah, I knew that logic was wrong somewhere. Looking back at this statement again, the logarithm of x is the power to which I've got to raise 10 to get x. Yeah, okay? And that's an example of where we found it. Okay? So in other words, this is a way to turn a number into a power. We can say 5 equals 10 to the power 0.699. Yeah, to the base 10, that's right. We tend to use logarithms in some functions, particular one's called the exponential function. Then we use this natural number e, so log to the base e, which is a natural log. But to do problems like this, power functions, we would use base 10. So that button on your calculator, that logarithm button, assumes it's base 10. The base isn't important. This is the important number. We're turning any number into a power of 10. So we're turning the number into a power. By doing this, we can then use, let's make sure I'm recording this. So, I am recording it. So by doing this, we can use the laws of logarithms or indices to help us when looking at equations. So now that our number, in this case 5, power, we can use the laws of logarithms or indices. Or logarithms, they're really the same thing, to manipulate functions. So there's two laws that are useful. The law of indices here, the first law of indices we're interested in is if I've got one power raised to another power, in other words 10 is to the power a and then the whole lot is raised to the power b, that turns into a multiply. So thinking of this in terms of logarithms, remember the logarithm of a is the power to the base 10 of a, and so that raised to the power b, and that's really equivalent to this, is just b times the logarithm of a. So in other words, I can bring this power down, the b, and turn it into a multiply, which is its use. Okay. The other one that's useful is 10 to the power a multiplied by 10 to the power b is 10 to the power a plus b. Add the powers. So therefore, as far as logarithms is concerned, the logarithm of a times b is the same as the logarithm of a multiplied by the logarithm of b. So we can multiply them. Added plus the logarithm of b. So in other words, you turn multiplication into addition. And similarly, 10 to the power a divided by 10 to the power b would be subtract 10 to the a minus b. So therefore, the logarithm of a over b turns out to be the log of a minus the log of b. So we use these three laws of logarithms when we're looking at functions. Okay? So let's look at our function. Let's go back to our problem. Look, we've got this function, p equals ri to the n. P equals ri to the power n. So we have p equals ri to the power n in this problem. The thing that's making it awkward is this power. We want to try and find this power. And so we could do with this power coming down and turning into a multiplication. In other words, we could do it using logarithms. So we can find out what this thing is. So we take the logarithm. We turn these into logarithms. If I want to turn this right-hand side into a logarithm to make it into a power, then I must also make the left-hand side, turn that into a logarithm. So I just turn them both into powers of 10 effectively. So the logarithm of b, or p rather, equals the logarithm of ri to the power n. I've logged both sides, we say, which is effectively turn them into a powers of 10. So, looking at this right-hand side and using the laws of logarithms, we can separate this out. Look, if I've got one thing, r, multiplied by something else, I to the power n, using this one, I can separate it and it becomes an addition. So I can use this law and say that the log of p equals the log of r plus the log of r to the n. Thank you, I to the n. And then we can look at this part of it, log of I to the n, using this one, means we can bring that power down and turn it into a multiply. And so then we can write log of p equals the log of r plus n times the log of I. Okay? So, going back to our original problem, which is here, we've got p equals ri to the n. So if we look at that original function, I and p are our variables. So I is the independent variable and p is the dependent variable. So in the original function, I was going to be put on the x-axis, p in the y-axis. So now we've rearranged this function to get this. Instead of plotting p on the y-axis, we're going to plot log of p. So this goes on the y-axis. Instead of plotting I, we're going to plot the log of I. So this goes on the x-axis. So that's my x and my y variables. And if we do that, we should get a straight line. So we can compare that with the equation of the line, which is y equals mx plus c. And if we look at it, this gives us, this is a constant. If r is a constant, the resistance, then the log of r is a constant. So that gives us the constant plus this n is going to actually be the gradient of the line. So if we plotted log p against log of I, we should get a straight line where m, the gradient of the line gives us the value for n in the function, and where it cuts the y-axis gives us log of r, the resistance in the function. So let's have a go at it. Log I, look, that's what's happened here. The current is here. And then log I has been calculated. So if you go to your calculator, I equals 2.2. Find the log of 2.2, and you should find it's 0.342. P is 116 at that point, so the power is 116. The log of 116 is 2.064. And so on. So the log of I and the log of P have been calculated and then been plotted. And you can see that once they're plotted, you get a straight line. So we can draw our straight line on there. And again, use autograph to find the y-intercept and the gradient. So the gradient gives the value for n, the power, and just we've got to be a bit aware here because this point here, whoa, what the hell happened there? This point here gives the log of r, and so we then have to find out, remember what this is a power of 10. This is 10 to the power r. So to find out the actual number, we've got to find out what 10 to the power that value is to find out what r is. Okay. Okay. So let's try one.